Hello everyone, welcome to Saimedha Koti, Hyderabad. In this session, I would like to discuss about gunshot bits in the induction machine for Genco AE exam. Let's start from the question number 1. The question 1 is, the nameplate of 3-phase induction motor reads as V equal to 400 volts, the power rating in HP equal to 5 HP, the frequency is the 50 Hz, the current is 15 amps, connection of the winding is delta, the speed of the motor is 540 rpm, the number of poles per which stator winding is wound, option 1 10, option 2 12, option 3 14 and option 4 the 16. And first one, here this speed is the rated speed of the machine. The speed rating mentioned on the nameplate details of 3-phase induction motor is the rated speed of the motor. So it is not the synchronous speed, rated speed of the motor, or it is also called, okay, this one is the full load speed of the motor. Full load, the speed of full load, the speed of the motor, and this is also the rotor speed, or this one is the rotor speed under the full load condition. So if you don't know the here, mention that frequency is given. So given that the frequency of the motor, the F is equal to the 50 Hz, but we need to find out the number of poles of the motor. So with we know synchronous speed Ns is equal to the 120 F by P, where F is a frequency and number of P is the number of the poles. So by using this formula we cannot find out. Why? Because this given speed is the rotor speed but not the synchronous speed. Then how do we find out the number of the poles of the motor? So from the options we need to verify the synchronous speed of the machine. So per P is equal to the 10 poles. So let us calculate the synchronous speed. Ns is equal to the 120 into frequency 50, the divided by number of poles is equal to the 10. So now this is equal to the 600 the rpms, the 600 rpm, and this next one per P is equal to the 12. So therefore Ns is equal to 120 into the 50 divided by 12. So now this is equal to 500 rpm, and similarly per P is equal to 14. So now this 14 Ns is equal to, so 120 into the 50 divided by the 14, the number of the poles. So now by solving this, so we can get the 120 into 50, so this speed is equal to 4 the 28 rpm. Now per P is equal to the 16 number of the poles, the synchronous speed is equal to 120 into 50 divided by 16 number of the poles. So this is equal to the 375 rpm. So now clearly mention that the name of the motor is a name of the machine is a 3-phase induction motor. Per 3-phase induction motor, per motoring mode of operation, the speed should be the less than the synchronous speed. The speed should be the less than the synchronous speed. Now by using this, we can verify. So per P pole, per 10 pole machine, here the speed of the machine less than the synchronous speed, and here this is the speed is a greater than the synchronous speed. Now this is also given speed is a greater than the synchronous speed, and this is also given speed is a greater than the synchronous speed. So this is only possible per motoring mode of operation. The remaining, so it is not correct. This one is the generating mode, and this is also generating mode, and this is also generating mode. So therefore per motoring mode of operation, in the options only 10 poles is a possible. So that answer for this question, option the 1 is correct. Okay, and next let us solve the question number Question number 2. In an induction machine is run at above synchronous speed, it acts as the synchronous motor, induction generator and induction motor, none of the above. So, this per generating mode of operation, the generating mode of operation, the speed of the induction machine, okay, the speed of the machine is greater than the synchronous speed, where n is the speed of the rotor, ns is the speed of the rotating magnetic field. So, where the speed is above synchronous speed, it acts as induction generator. And next let us solve the question number 3. The peak value of the phase MMF is pi maximum. Then the peak value of the rotating field caused by the 3 phase is 1.5 times of the F max, the 0.5 times of the F max, and 3 is the F max and 4 is the 3 max. So, where in let us assume the F is this F max is the maximum MMF, okay, maximum the MMF or ampere turns. So, let assume the phi maximum is the maximum flux of the motor. So, we know the resultant flux in the resultant field, okay, in the stator. So, this is equal to 3/2 times of the the MMF maximum cos theta minus omega t. Suppose in terms of the here, this is in the resultant MMF. Suppose in the flux point of view, this resultant flux in the stator is equal to the 3/2 times of the phi maximum, the cos theta minus omega t, where theta is a physical displacement angle and omega t is a time displacement angle. So, now this is equal to 1.5 times of the maximum flux, the cos of the theta minus omega t, where theta is physical displacement angle and omega t is a time displacement angle. So, that answer for this question option 1 is correct. And next let us solve the question number 4. The low power factor of induction motor, the at load, the results from high speed, the low magnetizing current of the no load current, high magnetizing component of no load current, high the working component of the no load current. So, this answer can be solved by using the vector diagram. Suppose this is a field flux phi 1 and this one is applied voltage V1. So, initially let us assume this is a magnetizing component of the current 1 and this one is a iron loss component of the current IW1. So, vector sum of these two, so we will get the no load current of the motor I01. So, this angle is a theta naught 1. So, actually in the machine practically it is in the order of the pi% of the I rated, okay, I rated valve. So, now let us assume this, let assume this is also the pi% of the I rated valve, but practically it is not correct, okay, practically it is not correct, but practically it is in the order of the 25 to 35%. So, 25 to 35% means, so it is a very high as compared to this one. So, this one is the magnetizing current I mu 2. So, this is equal to the IW1. So, IW2 values both are equal. So, now this is the 25% of the rated current I rated valve. So, this is the vector sum of these two. So, we will get the no load current I02. So, now this is the theta naught 2 values. By using this vector diagram, so this one is the due to the rate, this one is a magnetizing current, due to high magnetizing current, the magnetizing current is a very high as compared to the iron loss component of the current. So, this no load power factor angle, okay, this no load power factor angle is the high values, okay, this is the no load power factor angle is I. So, now when no load power factor is angle is high, what about the cos function? The cos theta is a low. So, this is a very low values. So, now if it is the power factor is a low, question is given in the reverse manner, the low power factor of induction motor at low loads results I magnetizing component of the current, okay, magnetizing current of the no load current, so that Option the 3 is correct for this question. And next let us solve the question number 5. So if the air gap between the stator and the rotor of induction motor increase, then the no load current decrease, leakage reactance are increase, the leakage reactance are decrease, magnetizing current is increased. So now this assume as okay, it is the stator of the machine, the stator of the induction machine, and in between there is a rotor, suppose here, so there is a rotor of the machine, shaft of the machine. So it is a rotor and this one is the stator, and this is the air gap between the stator and the rotor. So if air gap is increased, okay, then what will happen? So air gap, as if the air gap the between the stator and rotor, air gap length between the stator and the rotor is increase, okay, increase, then what will happen? This machine draws. So that is the reluctancy of the core, okay, reluctance of the core will be increased. So increased in the reluctance, so we know the flux is equal to the mmf turns multiplied by magnetizing current, ampere turns by reluctancy of the core. So increased in this reluctance, okay, increases the maximum magnetizing current. So this is the constant. So now this one is a flux is a in order to maintain flux constant. So it motor draws this is the motor. So draws the high magnetizing component of the current. So now that means magnetizing current will be increased. Okay, this one is a increase. So this is the one consequence. And next one, suppose if your air gap length is increases, the leakage flux, okay, will be increased. The leakage flux increases, okay, leakage reactance will be increases. So now leakage reactance is the representation of the leakage flux in the machine. As leakage flux increases, leakage reactance will be increased. So that answer for this question, the leakage reactance increase. So option the 2 is correct for this question. And next let us solve the question number 6. In a 3-phase slip ring induction motor, high starting torque is achieved by increasing the supply voltage, the increasing the supply frequency, the connecting the capacitor across the motor terminal, the connecting the starting torque resistance across the slip ring of the slip ring terminals of the motor. So this one is start in slip ring induction motor, the slip ring induction motor, the starting torque produced by the motor directly proportional to the sum of the rotor resistance and the external resistance. So in this case where the R2 is a rotor resistance per phase, okay, this is the rotor, the resistance, okay, per phase value, and where Re is a external resistance, okay, this external resistance, the per phase value. So as the external resistance increases through the slip rings, some value of external resistance is inserted in series with the inserted into the rotor, in series with the rotor circuit, then what will happen? This is the net resistance, net rotor resistance will be the increase. So increase in the net rotor resistance, the starting torque produced by the slip ring induction motor will be the increase. So connecting the star connector resistance across the slip ring induction motor of the terminals of the motor. So option the 4 is correct for this question. Okay, and next let us solve the question number 7. The power factor of induction motor at no load is around, so 0.18 lakh, 0.2 lakh, 0.5 lakh and the 0.2 lakh. So order of the magnetizing current, okay, in the induction machine, magnetizing current in the induction motor is equal to the 25% to 35% of the 35% of the rated current of the motor. The similarly order of the iron loss component of the current, so in the induction motor is equal to 5% of the rated current of the motor. So due to high magnetizing current, okay, due to the magnetizing current is a very high as compared to the iron loss component of current. So no load power factor angle is very low, okay, this very high values. When angle is high, So then what about the cos function? Cos theta is the very low value. Okay, this is the very low the value which is the almost equal to the here. This is the nearly equal to 0.1, the 0.1 lag. Okay, this one is a the 0.1 lag. Okay, this one is the lagging part. So why it is a lag? Suppose the this is the no load current I naught, okay, lags the applied voltage by angle, okay, theta naught. So this theta naught angle is the nearly equal to the 80 degrees, okay, near equal to the 80 degrees. That's why here 0.1 lag, but it is given which is the nearer 0.2 lag. So the answer for this question 0.2 lag is the correct one. And next one, question number 8, a double cage induction motor has better starting and running characteristics because two of the following conditions are satisfied. The inner cage has high resistance and the reactance. Inner cage has the low resistance and high reactance. Outer cage has high resistance and the reactance. The outer cage has long resistance and reactance. They are option 1, 2 and 4, option 2, 1 and 3, option 3, 2 and 3, and option 4, 1 and the 4. So suppose this one is the stator or rotor of the machine. Suppose this one is the air gap between the stator. So this is air gap, between the stator, and this is for example point I am taking one slot. So this one is the air gap between the stator and rotor. So this is the first cage, it is the one slot, slot 1 point, designing of the slot like this. So it is the exactly one slot. So assume as this one is the shaft of the machine. So now the slot which is nearer to the shaft, which is nearer to the shaft, that is known as the inner cage. This one is known as the inner cage, and the slot which is nearer to the air gap is known as outer cage. Outer cage in the double cage induction motor. So this is the structure of double cage, the rotor structure. So for example point I have taken only one slot. So this is the conductor size, the winding, inner cage, outer cage winding, and this one is the inner cage winding. So it is designed with a thin wire. This one is the thin wire. And this one is the design. So designed with a thick wire. This is the thick the wire. That means cross sectional area is a small. This is the cross sectional area. Area is the small. In case of the outer cage, cross sectional area so is a large in case of the inner cage. So when this is nearer to the air gap, so in outer cage, in outer cage winding, or so this one is for outer cage winding, outer the cage winding, then what will happen? So this cross sectional area is a small. So let us find out, this R is equal to rho L by A. When area is a small, then the resistance parameter will be high. So now this one is the resistance is the I, and what about which is very nearer to the air gap? So therefore the leakage reactance, this is the leakage reactance is the low value, this one is a high value, this is the high and this is the low value. So reactance is a low. So per inner cage, then what will happen? Per inner cage, the inner cage means inner cage winding, the winding which is nearer to the shaft, shaft of the machine. So this is our shaft of the machine. So now this the outer cage is nearer to the air gap. So here it is designed with a thick wire. So therefore R is equal to the rho L by A. When area is a large, the resistance parameter will be reduced. So that's why this resistance is a low and which is far away from the air gap. So that the leakage flux is a high and leakage flux, the leakage reactance is a high values. So now by using this we can, by using these conclusions we can answer this question. See the option number, statement number 2. The inner cage has the low resistance and high reactance. So this is the correct statement. And the outer cage has high resistance and low reactance. So this is also correct statement. So which answer is the correct? Option 3 is the correct. 2 and 3 statements are correct. The remaining 1 and 2 statements are wrong. And next let us solve the question number 9. In a 3-phase induction motor, if air gap length is increased, then what will happen? Option 1, magnetizing reactance is decreased and the stator resistance are increased, magnetizing reactance is increased and magnetizing reactance remains same. So as air gap length between the stator and the rotor, air gap length between the stator and the rotor is increased. So then what will happen? So this is a magnetizing current of the motor increases. So increased in the magnetizing current. So but question about magnetizing reactance. So we know that magnetizing reactance Xm is equal to the applied voltage divided by the magnetizing current. So applied voltage is a constant. So increased in the magnetizing current, then that decreases the magnetizing reactance. Therefore, the magnetizing reactance parameters of the induction motor that decreases. So, okay, this one is magnetizing reactance is a decrease. So, option the 1 is correct for this question. So, if question is about magnetizing current increases, but question is about magnetizing reactance. So, by increasing the air gap length between the stator and rotor, magnetizing reactance parameter will be decreased. Okay. And next let us solve the question number 10. A 50H, the 3-phase induction motor has full load speed of the 1440 rpm. The number of the poles of the motor is option 1 4, option 2 6 and option 3 12 and option 4 8. So here given in the question, given that the frequency f is equal to the 50 hertz. So now the speed of the machine n is equal to 14 the 40 rpm. So this is the speed of the machine is equal to the 1440 rpm. So but we don't know what is the speed what is the synchronous speed. This is the only rotor speed. So first one per 4 pole machine the P is equal to the 4. So now what about the synchronous speed? The 120, the 50 edge number of the poles is the 4. So it is equal to the 1500 rpm. So this is the 1500 rpm. Now next one, this is for the n less than the ns only. Now let us verify the per P is equal to the 6. Okay, ns is equal to the 120 50 divided by 60. Now this is equal to 1000 rpm. So which is the n greater than, given speed is a greater than ns. So it is not a motoring mode of operation. And per P is equal to the 12 number of the poles. Okay, given that 12. So that synchronous speed is equal to 120 into the 50 divided by 12. So 12 is nothing but, so this one is a 10, so that 500 rpm. So now this is also n greater than ns. Now if we consider 8 pole also, so then what will happen? Synchronous speed. So this is equal to 120 the f divided by 8. So it is a 750 rpm. So now this is also n greater than ns. Okay, this is the also not suitable for the motoring mode of operation. So per 3-phase induction motor only 4 poles is a possible. So therefore if we know this one synchronous speed, so we got synchronous speed, therefore the synchronous speed ns is equal to 1500 rpm. Now we require the poles. So this ns is equal to 120 f by p, that is equal to the 1500 rpm. So now p is equal to 120 50 hertz, okay, divided by 4 number of, so divided by 1, this one is the 120 50 divided by 1500, so 1500 rpm. So by solving this we will get, so 4 number of the poles. So answer for this question, the 4 number of the poles is a correct. Okay. So this was my 10 questions for preparation of AE exam. I hope you got it. Thank you very much.